Good morning, everyone. We're getting a little bit cooler weather, but then it'll get warmer again. So we're still enjoying the nice temperate climate. So I'm very happy for that, and I hope that it's lifting your spirits a little bit as you uh, get into the final section of our spring term. Um, Today, we're going to actually cover some college algebra topics. The first one will be parabolas, and then the second one will be ellipses. And I just want to let you know that I will not be available tomorrow during my conference hour. I have a jury summons that I have to actually abide by, and we'll see what that entails. Normally, if you're picked to serve on a jury and it's not a grand jury, it's a very short assignment, and I will let you know about that. But I'm going to add an extra day to the homework to give you some flexibility there. So if necessary, I may have to record a lecture for our Thursday class, and I'll let you know about that. But again, the summons I received like 3 weeks ago, and it has come due tomorrow. And right now, the Harris County is actually doing all of their court proceedings at NRG Stadium. So they've got COVID protocols in place, and so it's a very different setup. But I will keep you posted about what office hours will be available and what will ensue for Thursday. So just to give you a heads up about that, civic duty is important, and that's one of the things of living in America that we have to do. And it's a small price to pay to live in such a wonderful country. Okay, so what I want to do today is just again, the conic sections are an interesting topic, a useful topic. They pretty much venture into areas that you're already familiar with, but they give you some added detail that will be useful in engineering, useful in physics, useful in future math classes. And so it's nice to understand these curves from a different light. So let me go ahead and share my screen. So when it comes to the conic sections, you think, well, why do they call them that? Well, these are actually sections of a double napped cone. And when you take calculus 3, you will do quadric surfaces, which will be the three-dimensional analog of the conic sections. So it's not, not a wasted topic. So when we think about parabolas, we think about and conic sections like ellipses and hyperbolas, we think about a general quadratic equation. So when we start out, if we write down a general quadratic, I'm just going to do this. I had not planned to, but this is important. The general quadratic equation encapsulates all these curves. You can have a cross product term. We're not really going to focus on that. If we have some time to mention this, I'll come back to it, but rarely do we have the extra time. And we have quadratic in Y, and then we can have the first power in X. We can have the first power in Y. Again, the uppercase letters are coefficients. And then, of course, we can have a constant term. So it's like when we think of the general conic equation. So I'll just write this general conic equation. And of course, when you talk about the three-dimensional analog, you just add a bunch of extra terms that look like this. So the idea is that when we venture into this realm, we can think more geometrically in terms of intersecting a double nap cone with a plane, and think of a definition that would relate to the geometry. And then, of course, when we think about an equation, we think of analytic geometry, where we take the actual geometric construction and transfer it to variables. Because we know that when we're doing mathematics, especially STEM mathematics having to do with physics and engineering, We like to manipulate equations. So this will be the general conic, and we'll basically focus, I'll just say, this is the rotation term, and we don't usually say much about this. If I have time, I will mention it, but it's rather involved, but sometimes I can kind of encapsulate it and give you a short version of it. It involves trigonometry, obviously, because when you rotate a conic section, you think about radian measure or degree measure. But right now, so I'll just say this is a possibility. We'll focus here, the quadratic terms, the first power, things like this. So you're thinking, if we have an equation, then we can do the things to it that we would have done basically with the functions. That is, we can translate these curves. And so we're going to think about a translation of axes where we take the curve and we move it around, say to the right or the left or up or down. That will be a major construction that we'll do on Thursday. So the only other thing is when we take it and actually rotate it about an axis. That's a much more complicated procedure. So like I say, later on, if I have time to mention this, I will. It's an interesting topic. And when you take linear algebra, you can actually deal with this in a more general setting called quadratic forms. So for now, let's just go ahead and look at this equation and see how it impacts our first candidate, and that's the parabola. So we're going to imagine like we're Greeks, and we're going to describe this in terms of points in a plane. So a parabola is the set of points in the plane and move this mouse over. Set of points in the plane that is equidistant from a fixed point. So we're getting all these specified objects, fixed point. This is going to be called the focus, and a fixed line. You're thinking this is kind of odd. And the name for the fixed line will be the directrix. Directrix. Rarely will I write it out in all caps, but for right now, we have to call these objects by something so we can refer to them. So when you think about this, okay, parabola is the set of points in the plane that is equidistant from a fixed point and a fixed line. And you're thinking, okay, great, we can maybe build a machine that could do this. The Greeks were good at doing that, and maybe trace out a parabola. Okay, and that's fine. But say we're in a class where we want to work with this curve. We find this curve coming up in solutions to differential equations, and our professor says, okay, well, tell me something about this curve, and then you're hoping that you weren't asleep in pre-cal. So what we want to do is transfer this very simply to the Cartesian plane. Now what we're about to do is the result of, I'm sure, many efforts to simplify the process. So the key here is that what we're going to develop is what we call the conventional equation for the parabola. So maybe mathematicians started with this and said, okay, well, that's an equation, but boy, it sure is complicated. And we want to make it really simple. So what we try to do in mathematics is to create an equation like the equation of a circle that's user-friendly and gets the job done. So what we're going to do first is we're going to fix a real number. And this, when I say convention, or if I don't say convention, all of this is convention. So we're setting up the ground rules. So we're going to fix some real number. P, we're going to call it P. Uh, and this is an easy place to start. Now, what we're going to do when we fix this P, this will fix a point, and this will give us what we're going to call the focus. And we're going to place the focus, you know, we could either place it on the y-axis or the x-axis. We're going to start with the y-axis, and then we can flip all of this around with no effort whatsoever to have determined the equation if we had started here as opposed to here. So we don't have to do extra work. So we're thinking, okay, we're going to start right here. Now, of course, by writing this way, I'm tacitly assuming that P is positive, but I don't know that. But I'm thinking, okay, well, if it were positive, it would be here, and we're not going to lose any generality. We're still going to maintain the distances. So without loss of generality, we're just going to assume that we have a positive P. But notice I'm not specifying that. So you're thinking this would have an impact on the orientation of the curve. Maybe a positive P would mean that it would open upward and a negative P possibly downward. Right now, we're not really sure what that means. And then, so we fix this, and we're also going to fix the directrix. So we're going to set y equal the additive inverse of P. So this will be our focus, and this will be our directrix. And you're thinking, well, that's kind of odd. Why are we doing that? Well, okay, negative P, or the additive inverse of P, which is down here, we're just going to draw this horizontal line. So remember, this particular setup here is somewhat arbitrary in the sense that we have a fixed line and a fixed point. Okay, so if we specify the fixed line and the fixed point in a very simple analytic geometric way, that is in the plane where we can keep tabs on it, then we can set up the simplest equation possible. Now, if you look here, we know by this setup, even though it's kind of cheap, that the distance from this point to P and the distance from this point to the directrix is the same. So the origin here would actually be a point on the parabola. So we're just kind of working backwards and thinking this is maybe the most simple way we could actually start the process. And then, of course, if we were to move out some way, we're thinking the curve would have to start extending this way in order to preserve the distance here. So for instance, we might have a point here. Let me just kind of move this up a little bit just to maximize the space I have. Let's just say we have, just kind of eyeball it, a point right here. And so if we were to look at this distance here, and this distance, of course, the perpendicular distance to the line, we try to eyeball these as being equal, or at least congruent. So we could take this a point to be on the actual curve. So the idea is that if we were to plot several points, we're thinking we're going to start to get a curve that reminds us of a quadratic function, maybe something like this, just thinking outside of the box. Now, of course, there would be no reason to think, well, why couldn't we just move over to this side too? So again, let me just kind of eyeball this. We could do the same thing over here. We could use symmetry and just grab another point. So we're thinking, at least analytically, our curve maybe will look like this. We're kind of guesstimating. We're thinking as we move over to the right and over to the left, it's not going to be a line, but possibly a curve. But, you know, we're thinking, all right, so whatever we get, let's see what the algebra is going to be. And this is the simple part, at least for the parabola. So remember, as we start, you know, we can think of another point here. And then there's one thing that's going to be really important here. We're going to take a segment that is parallel to the directrix that runs through the focus. I'm going to draw it in red. This happens to be a very important object with the parabola. Of course, my drawing is a little less than symmetric, but we'll survive. So notice if I make this construct here, and I'm thinking, all right, well, what's going on here? If we look at this, the distance from here to here will be the absolute value of P here. And then, of course, another absolute value of P here. So, of course, we're not assuming that, if the P were actually negative, this would be 2 times the absolute value of P. But now as we look at this particular construct and we think about this, if we think about going all the way across, we get 2 copies of 2 times the absolute value of P. So if we went all the way across, this is what we call the focal diameter. This will be 4. Let me do this in the pencil. 4 times the absolute value of P. So when we look at this, again, we've got a point here on the parabola. We know this is 2 times the absolute value of P. So this distance here must be 2 times the absolute value of P. And if we take twice of it, we get this. We call this distance the focal diameter. Focal diameter. And you're thinking, that's not half bad, because once we determine P, we can get some simple points based on symmetry on this graph without having to work too hard. So when we look at this and we think about what's going on here, we're like, oh, simple way to get 2 points on the parabola just by knowing P. Very simple. So when we think about what we're doing here and we think about the construction of what's going on, this little red segment here, you're thinking, okay, well, someone decided that that was important and it's convention. So that's why Professor Ron is mentioning it. And it's not half bad. If we know P, we know the focal diameter. So that's a little extra thing. So over here, I'm just going to say, I'm going to shorthand it. I'm going to say focal diameter will be defined to be 4 times the absolute value of P, right there. So if a problem asked us to find that, we would certainly need to know what P was. So all that's left is to say, okay, how can we use this construction here with the actual definition to get a formula? Well, it's easy. And we're going to look at the square of the distance. Now, to make this easy, I'm going to label this point with a P, just call it P with coordinates X, Y. Focus is F0P. Let me recheck the focus. Focus, no pun intended, right? And then, of course, here, for this point, notice we have X comma negative P. We're going to call that D for directrix. Again, your choice in letters. So what's a common thing in analytic geometry, even though it seems to be a little bit long-winded, you have a label for the point and then the coordinates. So maybe we don't always have to write down the coordinates. So this would imply, if we just square the distances, the distance squared between P and F would equal the distance squared between P and D. Again, we could just have the regular distance, but since we just have 2 distances equal, we might as well go ahead and square them to rid ourselves of the radical. So this is like a circle equation. We don't write a circle in terms of the radicals because the circle is implicit. It gives us 2 radicals. It gives us an upper arc and a lower arc. So we're thinking this would be a more user-friendly way to write this so that it matches the general or the general conic equation. Okay, so we always have the ability to take square roots if we're looking for a particular branch. But if we want to adhere to the general conic, we want to eventually get a squared equation that has this form here. And you can see that this also describes the circle clearly. So now if we look at this, we're going to say, well, okay, x minus 0, well, we like 0. So we do the difference in the coordinates squared, and then y minus p, quantity squared. Now we can do the same for these 2 points, x minus x. Well, we like that. That's just going to be 0. That's always welcome. And now we have y minus the additive inverse of p, which is y plus p. And we square that. So now you can see that we can collect some terms and get an equation that's going to mimic this, but there'll be a convention as to how we write it, of course. There's always going to be that part. So let's see what we get. So now we've got x squared plus, so we'll square the binomial, y squared minus 2yp plus p squared. And on this side, of course, that's a 0. And then we get a y squared plus a 2yp plus a p squared, just doing the binomial squared. We did the binomial theorem in calculus 2, which is the more advanced theorem. We're going to do the positive integer result at the end of the course. So you'll be ready for calculus, at least the easy part of it. So now the y squares absorb. I mean, you know, we'll take what we can get, and the p squareds absorb. So we're like, okay, you know, this simplifies really nicely. And so what's left is that we've got an x squared term, and then we can just couch the minus 2yp over here with this one and get 4 copies of yp. So if and only if 4, and this is where we look at the convention and say, where do we want to put the p? Normally the p goes first and then the variable y. Just convention, but put it where you want, equals x squared. So this is what we call the standard equation in this form. Now, what do we have? We've got the directrix, we've got the focus, we have the focal diameter, and then, of course, this distinguished point, the origin, now at least with our setup, will be called the vertex, and it's always going to be at the origin unless we move this, unless we translate this like we're going to do on Thursday. So we have another point, which is basically like the vertex that we've already studied with the quadratic function. No need to call it something different. It basically identifies a maximum or a minimum based upon how the actual curve opens. So that's really what we've already been doing. So we're going to think of the vertex being moved around just like we did with quadratic functions. So when you look at this, you're thinking, oh, okay, this is all merging with what we already know about quadratic functions. But this particular construct does not assume that the independent variable here will be x. We could switch it to y and have the curve open either to the right or the left. So that's the flexibility here that we don't have otherwise, but we can always make any variable independent. So we're going to say this will always be a given that we don't need to compute unless it gets moved around. We'll call this the vertex, just like we did before. So when you think about all of this, you also think about the fact that we could have just fixed the p and we could have put the focus here on the x-axis. No reason why we should discriminate against the x-axis. I mean, what if we had done that? And clearly there's no issue here. All of this work is actually the same. We just have to move the p around. So if we thought about this, for instance, and I'll just do a quick sketch here of just setting up our algebra so that now we had the focus here instead. So we'd have focus P0 instead of 0p. And then we could do the same thing again, a lot less detail this time. And then we can think of the focal diameter here. And then, of course, the directrix now will be an equation that's vertical line. So we'd have x equal the additive inverse of p, as opposed to y equal the additive inverse of p. And then, of course, the vertex, that's not going to change. So this is where we get a twofer. That is 2 for the price of 1. That is, we don't have to do this again because all of this work is the same. We just move the p around. So here we would say we have a focus on the x-axis. We now have a directrix, which is a vertical line. All of this is the same. The focal diameter, I'll just write it again, but that's not going to change either. It couldn't. Now, the thing is, all we've done is switch the x's and the y's, so just switch them. We have 4px equals y squared. So the key here is the parabola is really pretty simple. I mean, we've got all of these objects running around that kind of can be a nuisance. We've got the focus and the directrix, so those are objects. You're thinking if you needed to draw a parabola, you don't necessarily have to sketch the focus and the directrix. You know, you can, the focus is nice because you can get 2 simple points using the focal diameter. That might be a freebie. So, but you could still get a real inexpensive sketch, kind of like you did with college algebra. But now that you have all this new machinery, maybe you can think of it differently. Now you can think of some of the attributes of the conic section and how certain physical characteristics make the study of the conic sections and their 3-dimensional analogs extremely useful to us. So now when you look at this, you're thinking, okay, when we do this type of problem, we don't have to worry about anything except, in this case, determine P. Determine P. That's the key here. So if you're given an equation and you've got, that's not translated, so you're not going to have any, you're not going to have terms where you have to complete the square, so to speak. But we've got basically a squared term, either an x or a y, and we have the linear term in the other variable. Okay, that'll be the giveaway. Not a whole lot of stuff, right? And then you're thinking you either have this one or this one when you have the non-translated case. And so you're thinking, well, not very difficult. And when we translate things, we'll have extra terms and we'll complete the square in one of the variables. And then with the translation equations, figure out what the new focus is and the new directrix and all that is. So for now, all we need to do is focus on our general construction, our general form of the parabola, and the pieces. So when I wrote determine P here, that's kind of the key. So this is like doing the identities with the trigonometry. We now have basically showcased certain attributes of the parabola. And we just want to make sure that if we're asked to compute these, then we know how to do it. So the key is the P. So let's look at a couple of examples. Now, I do admit this is a little on the simple side. And after all the trig we've done, this will be a refreshing change. So let's be happy for that. So let's look at some examples here. Well, let me move this over here. Got my Wacom tablet under my keyboard here, so I have less room to maneuver. I always like to use the tablet, but my document cam is superior. So here's an example. let's just see what we can do with this. Here, what we want to do is compute focus, directrix, and focal diameter. I'll write these out for now. Later, we can use some abbreviation. Now, again, we want to focus on the fact that we have these standard equations. So here's what's given. We have x plus 1/5 y squared equals 0. Now, this is where we're thinking, okay, well, we had two forms. We had two forms. We had the form where x was squared and we had the form where y was squared. So this implies we just think of the standard form here. We say 4px equals y squared. That's the standard form that corresponds to this equation. So we don't have to worry that this is not where we need to go. This is exactly where we need to go. So that's what we need to focus on. And then we're thinking, okay, this is when the focus is on the x-axis. So we have focus P0. We have directrix x equal the additive inverse of P. Just to write it down, you don't have to do it, but since this is new, just make a little summary of this. And then we have the focal diameter will be 4 times the absolute value of P. So when we look at this, we're thinking, well, we need, and this is complete flexibility, everyone. But if we focus on the standard equation, the problems turn out the same way every time. So we're thinking we've got to unencumber this 1/5 here. We need the y squared coefficient to be 1. So the first thing we're going to do is multiply through by 5 to move the 5 around. So we're going to get 5x plus y squared equals 0. So this is where we multiplied by 5. Multiplied by 5. And now the focus is to write this. So if we move things over, this will be negative 5x equals y squared. And this will be our standard. This is standard, so write standard. Now that we have the luxury of new equations, we can get the information a lot quicker. So there's our standard form. Now notice we're good to go. So if we look at this and compare it to this, we see 4p equals -5. That's the coefficient of x right there. So first, we're going to be lazy. This means focal diameter, which equals 4 times the absolute value of P, is just going to be the absolute value of -5, which is 5. So that's easy. That part is very simple. Again, if you like, you can just go ahead and move the absolute value to the 4p. I mean, you can write it this way if you prefer. Doesn't matter, it's equivalent. So either way you want to write it is fine, which will help you to understand why I did this computation. And now, of course, that makes the computation for P even that much simpler. If and only if P equals -5/4. So that's the value of P. So when I talked about doing these types of constructions, we really do need to know what P is. But since we've got the coefficient here already set up for the focal diameter, we can just kind of pounce on it and be done with it. And now this implies our focus will be what? P0 -5/4, 0. And now the directrix x equals the additive inverse of P. So we take the additive, let me just write it down. So the additive inverse of -5/4, which gives us a +5/4. So just writing it unencumbered, we have our directrix. Okay, so these make really nice test questions because basically all they do is just test you. It's kind of like testing you on trig identities. Or like when you took your general math, your number theory class, you might have done circles and you found the center of the circle and the radius, things like that, computations that require, well, and of course, you know, if it were written in the nice standard form, otherwise you would need some algebra. So that would have to probably carry you into an algebra 1 or algebra 2 class. So when you look at this, you can think, well, we could get a real simple sketch. Maybe we need a quick sketch of this with all these new constructions that we have. So let's go ahead and draw a cheap sketch. Again, this is not difficult. It's just a new way of looking at a curve that we already know very well. And for your study of curve theory, when you get to Cal 3, and then even some in Calculus 2, this is very helpful. It's nice to have different ways of looking at curves and different ways to manifest them algebraically. So if we look at this, we've got the focus. So let's spread this out a little bit. So we've got 1 and a 2, -1, -2, and then here we've got a 1 and a 2. So we'll say about here, -5/4, out right there. So we have focus, -5/4, 0. And then of course here we take the vertical line through 5/4. Again, this is just adding detail that we didn't have before when we did the quadratic functions, but we did have the axis of symmetry, which we still have. We just, you know, it's kind of clear from the focal diameter. And then of course we had this. Now, the thing about the focal diameter, if we look, it's 5. So we know if we go half the distance of the focal diameter, we can get a cheap point. So for instance, just take half of that, that's 5/2, 2.5. So we'd go 1, 2, 3. So here's a cheap point right here on the curve. And then we'll go 1, 2, 3, another cheap point, 5.5, out right there. So the focal diameter is a quick way to get 2 points on the curve that other than the vertex. So now when you look at this, we've got what? -5/4, 5/2. And you don't even have to necessarily label them, but we have it for free, -5/4, -5/2, just using the two absolute value P. This is 4, so we take half of it. So that's a real quick way to get 2 simple points. So now, you know, just go ahead and connect these like with the basic curve there. So just like we were doing quadratic functions, you know, just take your time so it kind of looks like quadratic. So there we go, right there. Again, just a real simple curve where now we can see this segment is called the latus rectum. I believe that's the Latin for it. I won't use that really. I just really want to know the length of it. And then, of course, as you do more engineering, there are lots of nice characteristics, symmetry characteristics of the conic sections that make them so valuable that we use in our everyday lives, especially the paraboloid as a means of making a loudspeaker or an automobile light by placing the sound or the illumination at the focus that will cause reflection of rays parallel to the axis of symmetry, which concentrates the beam. That's why when you look at headlights, you're blinded because you get a concentrated beam. And if you sit right by a loudspeaker, you're deaf because you get a concentrated beam of sound. So the conic sections and their properties have been known for ages. And of course, you can exploit these with other algebraic means and calculus means. So this always makes an interesting topic when you're bored and want to, look into things. If you ever think about when we talk about the ellipse, the Mormon tabernacle, where the choir sings is in the shape of the ellipsoid. And that's why the acoustical properties of that building are so remarkable and known worldwide. If you ever looked at the structure of that ceiling, it's a maze of wood and steel that again, to have created that was a work of art. So we are grateful to the Greeks who discovered all of this, and then we just took what they started and improved it a little bit algebraically, though it's not that interesting. Um, it's something that is kind of interesting when you think about how we take for granted all of these characteristics that make our life a little bit easier. Now, in the following example, let's see here. I just want to give you an example where we can just be given some other information and determine, for instance, what the equation of the parabola would be. So again, this is very simple, but this all depends on the convention that we have set up. Now, of course, there are probably other conventions that you could come up with that would do the same thing. But the reason we study these are universal conventions, and you will see them over and over and over again. So your physics professors will use these, your engineering professors, your math professors, worldwide. These are universal conventions, not like the inverse secant where no one can seem to decide on the actual definition. So if we had an example that looked like this, for instance, just change it up a little bit. We could say determine the equation of the parabola. Determine the equation of the parabola. And here's what we're given. We don't need much when it comes to the parabola. We're given the directrix. So we have the directrix x equals 1/20. I'm focusing on the fact where we have a different independent variable squared. You're used to the x being squared. That's easy. That anybody can do that. But we need to make sure that you're focused on this new construct where we have these curves opening to the right and the left. So first, this is the given part. So now you're thinking, you're exploiting the fact that there's certain objects that are defining objects for the actual parabola. So here you're saying, okay, the directrix is given to be this. So first you say equivalently, this is x equals the additive inverse of p, okay? That we know already. And then plus, what's the standard form? We did that on the last example. The standard form is what we're going to need to write the actual equation. So this will be the 4px equals y squared. And then you're thinking, well, do I have to make it look different from that? No, not at all. I mean, you can move things around and transpose things, but once you have an equivalent equation, you're done. You may want it to look differently depending on what you're trying to accomplish in a problem. But now you're thinking, well, again, we see that 1/20 is the additive inverse of p by the equation of the directrix. So if and only if the additive inverse of p equals 1/20, if and only if p is the additive inverse of 1/20. So we're like, okay, we can do this. Now, all we need is this construction and we're done. So you're thinking, maybe we should have lots of problems like this on the test because they won't take long. So, and that's true. Not every problem has to be so tedious. I mean, we understand that certain computations are more involved algebraically, but here we're just basically trying to introduce ways to solve problems with the conventional equations for the parabola. That can be very useful to us in this class and other classes. So now we're thinking, all right, now we can construct this. So we need 4px will be 4 times negative 1 over 20x. So of course, this is negative 4 over 20x. And we can just reduce this to negative 1/5. So we get negative 1/5 x equals y squared. So when you look at this particular example, there's really not much to do at all. You don't have to look at this problem like, oh, I've got to do some expansive calculation. It's like we're, they'll say, well, what's the equation of the circle? And you're thinking, well, what would you need to give us? Well, the radius in the center, and then you could write it down. Okay, so this is equivalent to that. So lots of times, just to test your understanding of the new objects, problems will be written this way, just so you're thinking, okay, well, now I can figure out the one quantity, that fixed number that pretty much defines the parabola. And you're thinking, well, could it have been another way? Absolutely. So it's not the case that this convention, someone just sat down in 5 seconds and said, this is the way it's going to be. These get adjusted and changed, and over time, they're determined to be very useful, very user-friendly. And then, of course, just like any type of principle, is eventually accepted as convention, which is the case for most of the mathematics that we study. I mean, you don't even have to be able to speak Mandarin Chinese if you've got a colleague that works in China and you're thinking, well, you can communicate through the mathematics. And then maybe in the communication, eventually learn a little Chinese, and then you can help them learn a little English. But the nice thing about the other countries, English is mandatory. You learn English because everybody knows people speak English. And then, of course, for most of you, you're already bilingual, if not trilingual. You know other languages. And so the understanding of other languages is a beautiful thing. But at least fortunately in mathematics, the notation is the same. The notation that you use in mathematics is just like music. It is universal. Okay, so now that we kind of have a different way of looking at the parabolas, let's think about another type of curve, which is really going to be a more generalized version of the circle. That's called the ellipse. So when you think of a circle, you're like, oh, that's a nice curved object that has a really beautiful symmetry. But then you can think about squashing it or stretching it to make an oval. Okay, and you're thinking with that type of transformation, and that's topological because you're not tearing the curve, you're thinking, how could you make a more generalized circle equation that of course would include the circle we all know, but also include the oval curves type things, the things that we see all over the place. We think of the ellipsoid, the tabernacle where the Mormon tabernacle choir sings. So we're thinking, how can we do that? Well, let's go back to the Greeks and depend on what they've done for us. So now what we'll do is think about ellipses. And this will be the same type of definition, but with a little twist to it. Now, again, we could make a contraption to sketch an ellipse, but what we want to do is, again, come up with an equation that's user-friendly that will help us to utilize this new object in an algebraic way. So here's what the definition looks like. An ellipse, and you may have seen this in a previous class, just like with the parabola, is the set of points in the plane is the set of points in the plane, the sum. Now this is kind of odd. The sum of whose distances, sounds like an English class now, the sum of whose distances from two fixed points. Now we have two fixed points from two fixed points is Now you're thinking, what are we going to call these fixed points? Well, that means we're going to have one focus and another focus, and the plural of that will be the foci. So those will be the 2 points. Is a positive constant. So we're thinking this is going to necessarily be a little bit more complicated than the parabola, because we were able to use that P to define the focus and the directrix, but here we don't have that luxury. We can't be that specific about the constants that we're going to have. So basically here, the 2 fixed points, we're going to use the same notation. I'm going to put a subscript on them for now. So what we're going to do is first, we're going to fix C positive and fix A positive. And we will, and define the foci. We're going to say focus 1. This is going to be symmetric about the origin. Again, we're going to be real lazy again. Focus 1 will be C0, and focus 2 will be the additive inverse of C0. So this is going to be symmetric around the origin. And the positive constant will be determined a little bit differently. The positive constant will utilize A, but we're going to make the algebra a little bit simpler and use positive constant equals 2A. Now this again is an adjustment to make the equation more user-friendly. And the thing is that as we were looking at some of the trig identities, I said, now, ladies and gentlemen, the negative here is convention, because it is convention to write a particular term first. And so that required us to have a negative in the sum to product, the very last equations we derived. Not because we were trying to rock the boat, but we know that that's how they're conventionally written. So we want to adhere to that. And basically, when the construction of the ellipse was considered in an algebraic manifestation, this turned out to be a better way to define the constant. So again, this turned out to be a convention, just like this did. So we've got our positive constant, and we're going to get a relationship between the A and the C that are fixed. That may not be obvious right now, but shortly will be. So you're thinking it might be a little bit easier to build a contraption to sketch the ellipse, because you're thinking you've got these 2 points, and you could think about building some type of curve drawer that could utilize some kind of chain or string or something to keep the distance or the sum at a constant. And that is a little bit easier to think about drawing than maybe the parabola. But again, that's fine. And as future engineers, some of you might want to build these contraptions. But right now we want to think of them mathematically, at least from the standpoint of algebra. So what we're going to do is we're going to be lazy again. Now, of course, the convention, now that we know about it, we can call it lazy, but it really is quite ingenious that this was determined to be a very useful way to describe this particular curve, which is going to be the generalized circle. So now, when we look at this, we're going to have the origin. And then, if you like, we're going to go ahead and just place focus 1 right here, focus 1. So I guess we'll have like a plus or minus C when we do our foci. I'm just going to label them now for the utility of the algebra. And focus 2 will be the additive inverse of C, 0. Now, here's one thing that's kind of interesting. Notice that we're symmetrically situated about the origin. And then this is where we can do some very simple algebra, which will be Pythagorean. So for instance, if we thought about a point on the curve here, And again, we've got these equal distances here. We could think about this distance here and this distance here, just to think about something simple. So if this were to be a point on the curve, this is where the 2A is very useful. We could think, well, this would have to be A and this would have to be A because this triangle is isosceles. So again, we're thinking, all right, so that would create a right angle there. And we're thinking, all right, so if this distance, we don't really know what it is, we could call it B. So for instance, if you like, you could just think for now that this would be a point 0B. So if we knew A and C, that would fix B by the Pythagorean theorem. So again, if we fix the A and the C by virtue of the fact that we have the definition of the ellipse, that's going to fix B via the Pythagorean theorem. So this would imply, at least at this point, that we would have what? A squared equals B squared plus C squared. The upshot here is that A is going to be bigger than C because these are defined to be positive numbers. So when we think of taking the square root property, we're not going to do plus and minus with the A's and the C's. We're going to think of the foci that way, but the A is an actual positive quantity. So this would mean that A would have to be bigger than C. And also A would be bigger than B too. Just as a little aside, A would be bigger than B. So what we're seeing here is that this is going to define B squared to be A squared minus C squared for free. So additionally, and we're just getting this just by thinking outside of the box. So now we're thinking, what does this mean? C squared equals A squared minus B squared, or B squared equals A squared minus C squared. And this may come in handy when we're trying to get a general equation. So we're thinking if our equation is going to be similar to that of a circle, this A and this B are going to be in there somewhere. And so we're thinking if we can figure out the A and the B from the general equation, we can always get at the C, which will define the foci. Okay, so we're thinking, this is kind of like we did with the P with the parabola, but a little bit more complicated because we've got two fixed numbers here. But what you see here is just a little analysis having to do with what we've already been treating with our what? Right triangles. So sometimes it's that simple. But now we have to figure out how all this is going to work together. So let's just say that we have a generalized point, maybe not that specific one. Say we have a point, say right here, that we determine or that we specify to be a point on the parabola, on the ellipse. We'll do the same thing we did before. Let's look at the distance between P and the first focus right here, and the distance between P and the second focus. So we see that P is an element of the ellipse. So again, we just, we're thinking with this construction, we'll get a more generalized circle. And for now, we're thinking, keeping our fingers crossed, that this is going to look like a circle, that we're going to get an x squared term and a y squared term, because we know the circle has both of those. So we are focused on the fact that our simplified equation will have those objects in it and give us some way to figure out the A and the B so we can figure out the C, which kind of is the crux of all of this. So what is this going to mean? So this implies that we have the distance. Now we can't do the squares this time because we got that blasted 2A hanging out. So we don't get all that. So we're going to have to square a couple of times. Now, what I wanted to do here is just show the derivation of this, not because we won't have to do it for the hyperbola because it'll basically be the same kind of derivation, but I want you to at least see it once because it's going to be the technique you learned in college algebra. And it is useful, and it's not very hard. It's just something that you should know. So now we'll say the distance between P and F2, and I'll just say this, you can set this any way you want to do it. So we'll say the distance between P and F2 plus the distance between P and F1, just using the labels because we're kind of lazy. The sum must be equal to the positive constant. Now, when you think about this and you think about what we're doing, the first thing you want to do is say, well, if I can go ahead and isolate one of these radicals, I can square and get rid of it. And so that's what we want to do. So now, if you look at this, you're thinking, if I isolate maybe this one and square it out, take this over and square, I can get rid of some radicals. So let's just do this symbolically for now. The idea is that when we need, we'll go ahead and fill in all the details with the coordinates. So equivalently, the distance between P and F2 equals 2a minus the distance between P and F1. Okay? So now let's square, and then we'll fill in all the details. So when we square this, and let me go ahead and, I know we've got this y-axis going right through there. I'm going to get rid of it. So let's square both sides. So we get d squared P, the distance squared between P and F2, and now we'll square the binomial. So we'll get 4a squared, and then we'll multiply these together and hit it with a 2. So this will be a negative 4a times the distance between P and F1. And then we square this. So this will be plus d squared P F1. So now when we look at this, we see that there's a radical here, no radical here, no radical here. So let's go ahead and fill all this in and then see what absorbs and then move on to the next squaring. So now we can go ahead and do our coordinate subtractions. So P and F2, so we're going to get x minus a negative c. So this will be x plus c, quantity squared. And then we'll do y minus 0. We love that, plus y minus 0. Real simple. Equals, so now we've got 4a squared minus, well, here we're kind of stuck. We don't have anything. We've got 4a, and we've got the distance between P and F1. That's all going to stay in the radical for now. And then here, let's go ahead and see what we get on this one. So we've got d squared. So we've got P, again, x minus c, quantity squared, plus y minus 0. Again, a simple term. So what does this give us? So we've got x squared plus 2x c plus c squared, just expanding the binomial, plus y squared, equals 4a squared minus 4a times the distance between P and F1, plus, go ahead and expand this, x squared minus 2xc plus c squared plus a y squared. The idea is that we're just waiting on this because it's all tied up in the radical, so it's not going to absorb anything. But notice x squared absorb, y squareds absorb. We love this. C squareds absorb. Hallelujah. less to deal with. We're going to have plenty to deal with when we actually have to square again, so we might as well help ourselves out. So now notice we got the 4a squared minus the 4a times this, and then we've got 4 copies of xc. So notice we've got 4, take this over to here, 4xc equals 4a squared minus 4a. Let me make sure that looks like an A. Times the distance between P and F1. Now we've got a 4 in everything, so let's just rid ourselves of the 4. So we get xc equals a squared minus a times the distance between P and F1. So we've got one more radical, so we're going to isolate this and square again. So now let's take this over and just transpose so we don't have the minus sign. So if and only if a, and I'll go ahead and get rid of the, well, I don't need, we'll square it, and so we'll get rid of the radical. So we get d pf1, I'm just holding off on filling this in, equals a squared minus xc. So again, square again. So let me, I'm getting close to the bottom of the page there, so I'll just go ahead and do this. So now, when we look at this particular part here, this is where we are. We want to square again. So this will give us a squared, distance squared, pf1. Now square this, so this will give us a to the 4th minus 2a squared xc plus x squared c squared, just squaring the binomial. Square, multiply, hit it with a 2, square. Now let's fill this in. So we've got what? A squared. So now we can just go back up here. I'll just compare it to this. We have P and F1, so we do x minus c, quantity squared, and then we have y minus 0, just like we did before. I just waited to do this. So this will be an a squared times, let's go ahead and multiply it out, x squared minus 2xc plus c squared, okay? So x squared minus 2xc plus c squared, and I'll just go ahead and, not go ahead and squeeze the y squared in. That way I don't have to write another a squared plus y squared equals a to the 4th minus 2a squared xc plus x squared c squared. So now multiply this out, a squared x squared minus 2a squared xc plus a squared c squared plus a squared y squared equals a to the 4th minus 2a squared xc plus x squared c squared. So now when you look at all of this, you're thinking, okay, we're home free. And we're thinking how this would have been kind of difficult if we didn't have all those other terms to absorb. So now notice these guys are gone. The minus 2a squared xc hit the road. Now what we want to do is get all the x's together and all the y's together, and then the non-xy terms over here. So notice here, just do a little connection bar. Here are two x squared terms. Let's put them together. So this is going to be x squared times a squared minus c squared. Just factor the x squared. So those get a check. And now the y squared term, well, it's kind of lonely. We'll just write it right here. A squared y squared. That gets a check. And now, of course, this term, we want to join the a to the fourth over here. So a to the fourth minus a squared c squared. So now we're getting the terms that we already knew were going to come up when we were looking at the right triangle. So the reason I wanted to do this, again, this is a very simple derivation that is at the heart of why we do analytic geometry. And you're thinking, if we have different structures, we can simplify some of this, but at least with what we have now, this is a straightforward computation. So now you're thinking, okay, we're seeing the a squared minus the c squared, which we knew was going to be defined to be what? B squared. So we already have that definition right there. So now remember, we'll square or we'll factor a squared minus c squared. So now that we're going to get our 1 here, which is going to make our equation so simple. So now we're going to divide both sides by this quantity. So we're going to get a squared, excuse me, x squared, a squared minus c squared, divided by a squared minus c squared. Again, non-zero by definition, plus a squared y squared, a squared minus c squared, and of course, 1. Now, notice we get a lot of things that absorb. These absorb. And of course, the a squareds absorb. So now we see that, and of course, remember, b squared we set equal to a squared minus c squared. So we end up with an equation that is super simple and looks just like a circle equation, which is what our goal was. So we're thinking maybe we could have cheated and kept our fingers crossed and say, well, maybe it looks like this. So now we get x squared over a squared plus y squared divided by b squared equals 1. So now we're thinking, all right, this has the generalized version that we needed. And then of course, if a equals b, then this is just the equation of the unit circle. So we're thinking, yeah, that's a good equation. And it generalizes the equation of the circle. Now, of course, if we completed the square, if we shifted things around, we could shift the center of the ellipse. So now we're thinking, when we do this, instead of this being a vertex, this just becomes the center of the ellipse, like we're going to have a center of a hyperbola, because we don't have any other way of really describing it. So we just call it the center, so to speak. So now when we look at this, we've got this construction, but note, if we have the generalized form, we can get the a squared and the b squared. So now we'll transpose and say, if we need the c, we just say c squared equals a squared minus b squared. So that kind of gives us this. So the key here is with the standard form, what does the standard form give us? It gives us the a and the b, or more generally, the a squared b squared. And then, of course, the a squared b squared in difference, oh, and of course we need a minus here, gives us the c, which defines the foci. So we're thinking, okay, when we do this problem, the key here is determining the a, and that's going to actually give us x-intercepts, and the b is going to give us y-intercepts, okay, as long as we're not moved around, okay? I mean, or maybe we'll have a new set of axes if we translate. And then the C will give us the coordinates of the foci, okay? So now we look at this and say, well, here's an equation to get the C. And then, of course, the foci, we're going to define as plus or minus c comma 0. And we're going to define the vertices. This is interesting. We're going to define the vertices in terms of the x-intercepts, plus or minus a. All right. So these are going to be called the vertices. And so you're thinking you're going to have this distance that contains the foci. We're going to call that the major axis, and the distance that doesn't contain the foci, the minor. So these are conventional objects, the foci, the vertices. So we'll say major axis will have length 2 times a. Again, a by definition is positive, and the minor axis, which will be defined by the y-intercept, at least at this point, will have length 2b. So now when we think about this, we're like, wow, this is really easy. Here's our generalized circle. So let's just go ahead and do a little cheap sketch. Nothing major, just a simple sketch here. So when we think about an ellipse, we think about, we're thinking elongated, not necessarily. Maybe it looks more like a circle. So that's where we're going to define eccentricity, just another measurement that we're going to take for the ellipse. So for instance, we'll have our, in this particular case, our foci interior. So we can say focus 2. You don't always have to draw where the foci are. You just maybe just know where they live. And then of course the vertices, we could say V1 is a comma 0. And you don't have to be so particular here. We're just saying, we're just giving them subscripts like we have for the foci. That's just what I'm adding. This is more than enough if that's all you're asked to do. Usually you have to do them separately, and they'll say, the order that they want, as far as the a first, then the additive inverse of a. And then of course here, this point will just be 0 comma b and 0 negative b. And of course, these don't have a label, but you can see that the minor axis is 2b and the major axis is 2a. Now remember, the way we've set this up, the larger denominator will always be the major axis. So of course it could be associated here if we had decided to put the foci on the y-axis. So this is just like the parabola. We could switch these and have it going in a vertical direction. So by our convention, the larger denominator will always define the major axis. So that's kind of important. That's our convention. Larger denominator defines the major axis. So that's our convention. And it's very simple. And we'll take it. We'll take it because there is no simpler convention for doing this. And whatever price we have to pay for getting a more generalized equation is certainly well worth it, because this is not as complicated as maybe you thought it would be when we started the process. So the key here, the key with all of this is, again, convention. We start out with an equation. Maybe we have to do a little bit more operating on it to make it look like this, where we can identify the a squared and the b squared. Again, we will gravitate to the larger of the denominators because that will define the major axis and the vertices. Again, this comment here is important because it is basically tied to the construction and the convention that we have basically implanted on this problem. Okay, so again, you're thinking, what if we just flipped all of this stuff around? What if we flipped the x's and the y's, and we had decided that we wanted to put the foci on the y-axis? Well, let's just write that down, just like we did for the parabola. Again, this is just bookkeeping. So if we want to switch things around and do something like this, Again, this is just icing on the cake, but it kind of gives you the nice little picture. These are great for note cards. You can put these by your trig identities. Again, we'll just do a little smaller depiction here. So if we have this ellipse, again, we're thinking of the foci being oriented vertically. So we'll have focus 1 will be 0, C, focus 2, 0, negative C. So again, remember, C squared is the same. It's not going to change. C squared equals A squared minus B squared. That's the relationship that we've established. Okay, so if we had started the process by putting the foci here on the y-axis, we get the same construction, but again, it's a twofer. So now here the vertex 1 will be 0, A, and then you can see how when we translate things, we'll have to change these coordinates. So V2 will be 0, negative A. And then of course we've got the B0 and the negative B0. So of course now the foci are 0 plus or minus C, and then the vertices are 0 plus or minus A. And the equation now looks like x squared over b squared plus y squared over a squared. Again, we are identifying the larger denominator with the major axis, but that also by our convention identifies the a squared. So when we say larger denominator defines the major axis, that is, this basically defines a squared. Okay, so when we're doing this problem, the a squared is going to be defined to be the larger because that's how we've set up our convention. Okay, so when we think about this, we're like, okay, that's a little bit extra material that we have to deal with the ellipse. So when we think about the ellipse, we'll probably have more stuff, a little bit more algebra to do, but the focus will be this simple equation. Then we move here. I mean, from here, then you can automatically think about the vertices, and of course the minor and major axes length. And then you can move up to here to get the C to give you the foci. So you're thinking once you have the A and the B, you know, and you've got it oriented correctly. Okay, the major axis is vertical. You can just sketch off the A and the B and then just draw it. Okay, so it's really, if you want a really fast sketch, you don't have to work really hard. And then we kind of think of the center here. Center is just being 0, 0. Even though it's not a real center of the circle, we just say, okay, if it's not translated, the quasi-center of the ellipse will be what? The origin. So when you think about it, ladies and gentlemen, what we've done is basically how we started out with the trigonometry. We made it as simple as we could, but to give us plenty of information. So now we see that all the stuff that's come before is consistent with this. All the stuff about quadratic functions is consistent with the new discussion of the parabola. All the discussion about the circle is now consistent with the new discussion about the ellipse. Okay, so all of this is fitting together. So we don't have to worry that we're going to come up against some, what they say, contradictions. So let's look at a couple of examples here. Oh, and before I do the example, let me go ahead and define what I was talking about, eccentricity. This is just another measurement of the ellipse that has turned out to be fairly convenient, and physicists like it. Differential geometers like it because it gives a sense about what the shape of the ellipse is. So we want to define, again, this is easy, but you know, you can define your own term. Maybe you want to define a certain other parameter about the ellipse. We're going to call it eccentricity, eccentricity, and short E. E, and this will be, by definition, C divided by A. Now, you might be thinking, who cares about that? Well, we've got this nice relationship up here. So this is why this makes sense. And this is going to tie together the relationship between A and B that we've been highlighting, but this does it in a way that seems to be a little off center, but it's actually correct. So when we define this eccentricity, we compute C, we compute A, these are both positive quantities, and we take the ratio. Why does this turn out to be a good measurement? Well, let's just see. Well, so eccentricity is C over A, and now we're just going to throw in some squares. So this will be the square root of A squared minus B squared, because of course C squared is that, and we can write A is A squared square root. So we just do a little cheap algebraic manifestation with laws of exponents to bring this guy in. And now we could see that the algebra is going to be convenient here. So if we divide by the A squared, we get 1 minus B over A quantity squared to the 1/2. Now, when you look at this, you can now make some observations here that are good. Notice when A and B are relatively close together in magnitude, then that's going to be really close to 1 squared, and we're going to say 1 minus 1 is close to 0. So we're going to say when E is close to 0, essentially 0, this is going to mean circle shape. Because when A and B are close in magnitude, then you don't get the deformation as much. They're closer, so you get more of a circle-like appearance. Now, of course, A being the larger quantity, if A is much bigger than B, so we can say in this case, when this term is small, that is A is much bigger than B, this is closer to 1. So we say E is closer to 1. So basically here we say A approximately B, and here we're saying A is a whole lot bigger than B. And so this means oval shape. Now, of course, this doesn't mean a whole lot. When you sketch it, you'll see this, and you'll see that if there's a big disparity between A and B, then you're going to get more elongation, okay? And if they're closer in size, then the deformation is much less. It looks more like a circle. So this isn't completely useless when you think about it. Just the little bit of algebraic manipulation here just says that, okay, this is something we could actually do. So what we just need to remember is the definition, C over A. All this other stuff, you'll see that when you figure out A and B. So this is just maybe a little more reason as to why this makes sense. And if you saw a value of E that's closer to 1, you're thinking, oh, okay, that's going to be more oval in shape. But don't guess, just look at the calculation and make that determination. But you can always go back to this and do the little routine that we did right here to make it real for you. Okay, so let's look at a couple of examples. Again, this is like you think about this and you think about what we're doing with these kinds of constructions, and you're like, oh, Professor Ron, we could have done this in college algebra because there's no trig involved here, but it's kind of elevated, but not really. So I think the idea is, depending on what we consider to be important, it makes a little bit more sense to kind of shove this into the pre-cal where you've got a little bit more elevation in your thought process. So now let's look at an example. So say we want to do the following. Let's say here's an example. We'll just start out with a simple one. We'll compute the vertices. So I'll say compute vertices, foci, eccentricity, so vertices, foci, eccentricity, and we'll say Lengths, this is just lots of words, lengths of major and minor axes. So kind of like with the parabola, we have a few more objects to worry about, but they're not difficult. So remember, we're thinking the standard form for the parabola, we got the x squared or we got the y squared, but so now they're both squared. So there's less confusion there. We just have to figure out where the larger denominator is. And then boom, we know where the major axis is. Is it vertical? Is it horizontal? So here's an example. 2x squared plus y squared equals 4. So we don't kind of look at this and jump to the standard form like we did with the parabola, because the standard form is a little bit harder to get. We're not just looking, oh, the y is squared, so we know which one we're going to have. So at this point, all we want to do is get the 1 here, because we know the standard form requires the 1 on the right-hand side. So the first thing is go ahead and divide by 4 or multiply by 1/4, your choice. So 2x squared over 4 plus y squared over 4 equals 4 over 4, or 1. So when it's not translated, ladies and gentlemen, you don't have to complete the square, and the work is a lot more straightforward. So now what does this say? So the 2 will absorb into the 4, so we get x squared over 2 plus y squared over 4 equals 1. There's our standard form. So now when we look at this and we think about what it is we have to do, what's important here is the following. The larger denominator is found to be 4. So that identifies where the major axis is. It's going to be vertical along the y-axis. So now from this implies a squared equals 4. And we can just say major axis, just write it down, vertical. No need to not write that. Just say, okay, now we know how these are spread out, so to speak. B squared is 2. So again, this will give you the y-intercepts. This will give you the x-intercepts. And then c squared equals a squared minus b squared. This is so simple, it's difficult because it's a little bit unusual based on what we've been doing, but very, very trigonometric-like, where we're just tied to equations. With trigonometry, we had all these identities. Now we just have these formulas that aren't identities, unfortunately. So we have to really be very respectful of them. So now this will be what? 4 minus 2, which is 2. So this implies that we extract the positive square root. C equals square root of 2. All right. So now what does this give us? We'll have the foci will be 0 plus or minus c root 2, because again, these are situated on the vertical axis. Again, a will be 2. If you want to write here, just kind of to the side, a by definition is the positive square root of 4, and b by definition is the positive square root of 2. Just you want to add those, okay? And so now the vertices will be 0 plus or minus 2. So when you think about this kind of construct, you're like, this is no more difficult than the parabola, and we don't have a what? We don't have a directrix. Now, if we look here, we got the foci, we got the vertices. Let's go ahead and type this in. So 2a will be 2 times 2, which is 4. That's the major axis, major. Well, I have to write out major axis. And then 2b is 2 root 2. This is the minor axis length, minor axis. So we got that, and we just need the eccentricity. E will be A over C, or excuse me, C over A. Always remember A squared minus B squared. And so we've got C, which is root 2, over A, which is 2. So we could write this, if you like, as 2 2 squared over 2 to the 1/2. Just square that, and that'll just be what? 1/2 square root. The idea is this is fine here, but you need to be able to do manipulations like that. You saw that in your trigonometry. So we just square the 2 and then put it under the umbrella of the square root and then write it that way, which is exactly equivalent to that, which is the way I like to write it, 1 over root 2. I mean, this is just 1 over root 2. So the key here is, again, sketch is trivial, but the main thing about this is standard form. The larger denominator identifies the major axis, identifies the a squared. And of course, that gives you the disposition of the major axis, where the foci live. And so when you have that, that shoves all of these components of these coordinates of interest into the y coordinate, okay? Now, let's look at a couple of examples where we're given interesting stuff and we have to figure out the actual equation of the ellipse. So let's try one of these. Again, this is kind of fun if you think about it, a little bit different. And will certainly have its rewards as you take physics and more engineering and the curve theory that you're going to get in Cal 3. So let's see here. Compute equation of the ellipse. Compute equation of the ellipse. We're going to do the same thing for the hyperbola on next class. So it'll be very similar to what we're doing here, but with the hyperbola, we're going to get slant asymptotes, which is really kind of a crazy idea without a rational function. So here's the given, excuse me. The given here will be foci 0 plus or minus square root 10. And the vertices, so we got to have a little bit more information than we do for the parabola. So this is the given. So as long as we can figure out the A and the B and the C, we're good. We can fill in all of the parameters that we need. So notice now that this is like the last problem. We see that the major axis is situated vertically because all of these are shoved into the y coordinate. So this implies, we can go ahead and write it down, x squared over b squared. So now we can do this, y squared over a squared, where a squared identifies the larger denominator. Okay, so we know we have this standard form, so all we have to do is fill it in, and that's the easy part. Now, the beauty is that we have A and C, and we're good to go. So from the theory, B squared equals A squared minus C squared, or C squared equals A squared minus B squared. But since we know A and C, we're good to go. So this is A and this is C. So we have 7 squared minus the square root of 10 squared. So this gives us 49, and these are easy numbers, so I don't have to write this as a difference of squares. I like to factor things, but these numbers are so easy. Minus 10, which is 39. So this implies x squared. Again, if you think about this, we can go ahead and find intercepts we don't need. This gives us our b squared, so we have 39. And then, of course, our a squared is 49. And that's the standard form. Now, here's what's interesting about this. These equations look rather unfriendly when you think about it. But if you've got something like this, you can figure out these quickly. So what we did with this problem is we're given certain parameters about the ellipse, which identifies, in this case, the C and the A, And then we can get the b because of this equation. So this relationship here that we found from the triangle at the beginning of our conversation is really central. And remember, the a and the c are by definition positive. Okay, so when you're doing this square root principle, a is not plus or minus 7. Okay, a is defined to be the positive square root. C is defined to be the positive square root. So again, what we're seeing here is just a little interplay between all of the fixed numbers that we introduced to get the ball rolling. So how do we start out? We had to fix the a for the positive constant, and we had to fix the c, and both positive, for the distribution of the foci. And then from that, everything started to unravel, and we ended up with these nice simple equations. Now, here's an example that I think is kind of interesting. Let's look at one where we're given a different set of ideas here. Maybe we're given different parameters. So this will just kind of test what we did in our derivation. So kind of the derivations are a little bit important, because at least when you see the derivation, you see where all these ideas come from. Otherwise, it's like, okay, here's what you do, and you do it, and it doesn't really sink in. So now kind of in your mind, you're thinking about how we set up the process, and hopefully it'll move into your long-term memory. So in this case, example. So what we want to do is compute the equation of the ellipse. And in this case, here's the given. Eccentricity equals the square root of 3/2, and, well, actually, we've got more than this. Then this is important, more stuff, so to speak. We have foci on y-axis, and then length of major axis is 4. Okay, so when we think about this, we have lots of information, and we can just kind of pull everything together. First, let's just go ahead and say the foci are distributed vertically. So that's already going to give us x squared over b squared plus y squared over a squared equals 1. That is the form that we will have to abide by. Okay, so we already know what the form of the equation must be. And now let's see what we have here. E equals c over a, which is square root 3/2. So if and only if c equals square root 3/2 times a. All right, so boom, right there. So we've used that part, we've used this part, and now the length of the major axis, that's good. So again, this implies that 4 equals 2a. That's the length of the major axis, if and only if a equals 2. So now what we see here is we can easily get the b. We've got the a, we can get the b squared. So note, c equals the square root of 3/2 times a, which is 2. So this is square root 3, if and only if c squared equals 3. So now when you think about this particular setup here, it doesn't really matter how you do it. You can think, well, you can just go ahead and feed this in, but now that we've got the c squared, we're good to go. So then, and so my order here is certainly not unique. And you can do this problem many different ways, but this is kind of simple. So now then b squared equals a squared minus c squared. So a squared, again, is 4. C squared is 3. So we get a 1. Well, how simple. If and only if In this case, we go to our standard form, x squared. Now, of course, if you want, ladies and gentlemen, you can write a 1 here, but you don't need to. So just x squared plus y squared over 4 equals 1. Now, this is, again, this is easier than trigonometry, but the beautiful thing about this is that it offers us a new way of looking at structures that we really have thought about throughout our careers in math, or your careers, obviously. So when you think about what you did in high school geometry, one of the major philosophies that just transformed mathematics was the creative genius of Rene Descartes, because he was the one who formulated the Cartesian coordinate plane. And so now when we think of transforming the geometry to algebra, we call that analytic geometry. I mean, there was a time, and there still is, it's still the case. The calculus book I used at Carolina had a big chapter just on analytic geometry. I mean, and it's like, learn this. But half the time, what the professors would say, okay, well, you should have learned that in pre-cal. So, you know, go ahead and read through it if you need it. But the calculus text was basically purporting that don't forget this. It will be useful material later on. And so when you get to calculus, it might not be that you use this with every problem. And it may be just several weeks before you even get to some of this. But the second time you see it is easier. That is, if you don't have to look at this fresh for the first time, the second and third times are easier. Now, the very last example is very simple, but a very interesting problem. Now, here we've got k is positive, and it says the foci are the same for all values of k. The foci, here's a nice statement, the foci are the same for all values of k. And what's neat about this is that we just use the theory of the ellipse. And so when we write this, we have x squared divided by k plus y squared. You could construct this, 9 plus k equals 1. This is the given. So what's interesting about this, and you can actually test this out. And so the problem here is compute foci. So again, we don't have to rely on the fact that in this particular case, what do? Well, we got the theory. Notice k is positive, so the larger denominator is 9 plus k. So by theory, a squared equals 9 plus k. And b squared is just k. I mean, if you think about it, by deriving the equation, we now understand the algebra of the standard form. This is standard form right here, but it's not written in a way that we normally characterize it. But that doesn't invalidate anything. So now notice here, c squared equals a squared minus b squared. So this will be 9 plus k minus k, which is 9. And then, of course, c squared is 9, so we extract the positive square root for c. c equals what? 3. Now, of course, the larger denominator is associated with the y term, so this will be if and only if the foci are 0 plus or minus 3. So this is what I want to emphasize about what we've done today, albeit much simpler than trigonometry. When you think about it, the sines and the cosines keep us very busy. I had a student who decided that she wanted to go ahead and go into computer information systems. She said, Professor Ron, she says, I don't have your math ability. And I told her, I said, we all have different gifts. I said, but you are certainly capable of learning any math you need. But her comment was that, oh, there's so many things, and I really enjoy computers, but I enjoy certain aspects of computers that don't use so much math. And I said, well, just know that you have the background to always add to that. She decided to get into the computer information systems instead of just the computer science degree. But again, this is really important. Maybe as you're working through your career educationally, you make a few adjustments, because maybe right now there's certain things that are going on that keep you too busy and thinking you've got to make a little adjustment. So down the road, you can say, life is easier. I'm ready to go. I'm going to go back and I'm going to complete that degree. So I'm very happy when I hear students bringing peace into their lives. Ladies and gentlemen, it's hard to do anything when you're stressed all the time. And of course, a math class, a STEM math class like pre-calculus, keeps you really, really busy. And so the idea is that sometimes we have to make adjustments in our lives to make life more successful. And so I was very respectful of that. This student again, that sends the WebAssign messages and is just always so positive, and has endured many hardships through this pandemic. So I'm very happy for her that she's going to have a very successful career. And so just remember, if you have to make adjustments in your educational process, that's okay. Think about Professor Ron. I got my bachelor's degree, and then I did music for many years. I knew, and again, that's my other love other than mathematics. And then I knew there would come a time when I'd go back to graduate school and do my advanced degree in mathematics. And that worked out beautifully for me, basically because it was the right time. Okay. So I understood exactly what she meant. So just remember, if you have to make some adjustments in the process of education, that is certainly fine. That is certainly fine. But I will say this, it was very interesting to attend the Texas A&M University in College Station as an older student, when all of my colleagues were, I called them kids. I said, well, kids, have you done your homework? And they always laughed at me because they thought, oh, who's this dude? Is he the professor? So the thing is that don't ever feel that making adjustments in your educational process is a bad thing. It can be the boost that you need. So I appreciate your attendance today. I hope you've enjoyed our little excursion into parabolas and ellipses. We will complete with hyperbolas, and then we'll do a translation of axes. I'll be in touch with what the jury duty requires of me. If I have to do a recorded lecture for Thursday, I'll let you know about that. But that'll just depend on what service I'm required to do when I report tomorrow. So you all have a great day, enjoy the weather, and I'll see you during my office hours. Take care.